So now we're going to move on to a rational function. So recall rational functions, could be some restrictions from the denominator. So let's look at the denominator here. We know that the denominator in this case cannot equal to 0, so x cannot equal to 0. It's not part of the domain. What that looks like on graphical is it could be a whole or it could be a vertical asymptotes. And in this particular case, it's going to be a vertical asymptotes because there is no common factor to the numerator or the denominator. So let's actually figure out the critical numbers and then critical points. So to find critical numbers, we're going to have to find the derivative. And in this case, we're going to be using the quotient rule. And if we finish it off, we end up getting derivative of the top, which is 2x times x, and then minus the derivative of the denominator, which is 1 times x squared plus 1. We end up getting x squared minus 1 over x squared. So this is our derivative. And to find critical numbers means two things, where the slope is 0 or the slope is undefined. Now, in our particular case here, in order to find the zeros of a rational function, the zeros of a rational function come from the numerator. So if I have to show you my work, I would solve for this one first. In other words, I'm going to take x squared minus 1 is equals to 0. Now, if you want to find where the derivative is undefined, I put here undefined, you're going to have to look at the denominator where x squared is equals to 0, because when it comes to the rational function, to find undefined x values, it comes from the denominator. So let's solve for this. We end up getting positive 1, negative 1, x equals to 0. So that's our critical numbers. These are CNs. Now the question is, are they critical points? Well, if I sub x equals to 1 into the function, do we get a y value? And in this case, we do get a y value. For x is negative 1, we end up with a 2, negative 2, positive 2. And if I subbed in negative 1 into this function here, the original function, I end up getting a 2, negative 2. So one's a positive 2 and one's a negative 2. But what about this one here? Well, if we try to sub in x for 0 into here, it's going to end up having an undefined because we already established that this here is a vertical asymptote. So once we establish the critical points, which we just did, let's figure out whether things are local max or local mins by setting up the first derivative test. So remember what I said, we're going to have to set up the critical points from lowest to highest, negative 1 to positive 1. And here is our f prime. Now the question right now is, do we test numbers from each of these intervals? And the answer is no, because if you look at this, we're restricted. We cannot choose a number to the left of negative 1. It's just a coincidence that my critical number so happens to be at my endpoints. In this case, I'm going to block this off. We cannot choose numbers to the left of negative 1 based on the restrictions. We cannot choose numbers to the right of negative 1. So the question is, well, what's left? Well, we can only choose a number in between. So now when you set up your interval table, there's one thing that I kind of forgot, and I should actually stress on it. You need to include all your critical numbers, and that includes all your vertical asymptotes, because this 0 is a critical number. So all these are critical numbers. So over here, I'll put a dotted line here because we know it's a vertical asymptote. I'll call it a VA, or I'll put here the slope is undefined. And you just check the slope to the left of 0 and to the right of 0. And if you sub a number such as negative 0.5, you're going to get a negative. And over here, you're also going to get a negative. And when you sub the derivative, when you sub these numbers between here into your derivative, which is this one over here. So what that means is graph goes down, graph goes down. So the question right now is, are these 2 points turning points? And the answer is no, because we don't know what's happening. We know what's happening to the right of negative 1, but we don't know what happens. We don't have any information to the left. So we cannot say it's going up and then down because we have no access to this. Same thing for here. So in this case, these 2 points are neither turning points. They're not local max or local min. So the next thing is, well, fine, there is no local max and local min, but is there absolute max and min? So let's look at the endpoints here. So these are the endpoints or the critical numbers, and one would say, okay, well, it seems like 2 is the highest y value because absolute max is the highest y value and negative 2. Oh, so this could be a potential absolute min. But the question right now is, hold on. We have to understand something about this function. To start off with, vertical asymptotes. So remember in advanced functions, you should have learned something about vertical asymptotic behavior. So what that means is, well, what is happening at the vertical asymptote to the left and to the right? And do we know what's happening? And the answer is yes, because we know the slopes to the left and to the right of the function, to the left and to the right of the vertical asymptote. So recall that vertical asymptotic has a couple of features. So while sometimes vertical asymptotes, the behavior, maybe it could be a unidirectional, meaning both arrows go up, or they could both go down, or maybe you can have either one of each. It could be this one here or this one here. The question is, well, what do we have in this particular function? Well, if you look at the slopes here, the slopes are both negative. That means from left to right, the graph is going down. So in this case, it seems like this one here would be the appropriate one because the graph is going down. Now the question right now is, which of these has a slope of a negative slope from left to right? So it's this one here that seems to have a negative slope going from left to right. So based on our first derivative test and based on the sketch near the vertical asymptote, this is what the behavior looks like. So what's happening near the asymptote, vertical asymptote? So it seems like the graph is always going down to the left of that vertical asymptote. As I get closer to the vertical asymptote from the right, it seems like the graph is going up. So in this particular case example, there is no absolute maximum because you don't know what the defined highest y value nor the lowest defined y value minimum here. In other words, this function has no absolute max or min. So just to modify this question, if I had removed the restrictions, what does that mean? Well, what that means is we can actually lift off this part here. So I'm going to erase this part if there was no restrictions, and therefore we can actually continue on this question to the left of -1 and to the right of -1. And if I did that here, what's going to happen is that my slope here would be a positive, and over here, if I have to put a number to the right of 1, I'm going to get a negative. In other words, the behavior goes up and then down, then here goes down and then back up. So if I open this up, meaning no restrictions, I could say, based on the modified question, that this is a turning point. This is also a turning point. This is a local min, and this is a local max, based on this unrestricted function. However, just because I changed the question, will we still have an absolute max or min or not? We won't have an absolute max or min because of the vertical asymptote behavior. So now we're going to move on to an exponential equation. So let's look for the critical points and classify the critical points as local max or local min. So as I said, we're going to find the derivative first by setting each to the derivative equal to 0. In this case, to find the derivative, we use the product rule. So 2x times ex plus x squared. The derivative of ex is itself. And we need to clean this up, unlike previous units where I asked you don't have to simplify, but now because we're solving for the zeros, we're going to have to clean this up. So I see a common denominator, a common factor, and also a single x. So we're going to factor out x ex, and if I did that, I would have 2 plus x. So, and we don't have a denominator here, so in this case, to find critical numbers, we don't really have to worry about finding where the slope is undefined. We just have to set it to equal to 0. And because there's 3 factors, x is equals to 0, ex equals to 0, and 2 plus x equals to 0. This is an exponential function. If you keep on going, you're not going to get an answer for here, no answer. So that means we have 2 answers, x equals to -2. We do exactly the same thing, so now we have 2 critical numbers. We're going to have to figure out whether there's a point, and you sub this 0 back into the original function. We get a y is equals to 0, and here we get 4 is equal to e to the power of 2. So that means these are actual critical points. They're actually dots on your graph. Now the question is, are they turning points? And if so, are they local max or local min? We do the exact same thing. We set the critical numbers from -2 and 0. And I'll put here f prime, and this is your function. You can put x ex 2 plus x, and then you sub in some numbers between the intervals because we're unrestricted. So in this case, this is going to be xer. The reason why I know is because this is a combination function. A parabola, the domain is xer. Exponential function is xer. So because their domain is xer, I know this function is xer. There's no restriction. So then we have to sub the numbers in, and what do we get at the end? We're going to end up getting And we end up getting the following sign. So what that means is the graph goes up, flans off, then down, then flans off, and then goes back up. So we can conclude right now that this here is a turning point with a local max, and this one here is a turning point with a local minimum. Now the next question is, does this function have an absolute max or min now that it is open? Now based on the way that this sketch looks, so it's always good to sort of like sketch what this graph looks like. It goes up and then down and then back up. So we look at the end behaviors, which is over in this area here. So it seems like as x goes to the right, the slope is positive, meaning the y values are going up. How it goes up, we don't know. It could be going up like this way. It could be like flattening off. We don't know exactly what's happening, but I know for a fact that it's always the y values are going up. And because the y values are going up, we don't know exactly where it stops. In other words, there is no absolute maximum. Now over here, if I go reverse to the left, all right, if you notice here, the graph is going down. Now how it goes down, I don't know. It could flatten off, it could go steeper, it could just go whatever it is. But I know for a fact that if I go to the left, the y is going to go down. I don't know how low, but I know that it's not going to stop at a defined point, and therefore there is no absolute minimum. So I'm going to call this example a bonus example because you're only responsible for polynomials, rationals, and exponentials. You are not responsible for, I'll call this irrational functions. So this would be like a bonus, and if you don't feel like watching example 4, you can just stop. But I'm just going to continue on. So over here we have a irrational function. We don't know what it looks like, but we know that we can figure out the derivative to find the potential turning points or local max. So just using the power rule. Now, when we have a function like this, I know for a fact that there is going to be a denominator in the x, meaning that if you want to find the critical numbers, there is going to be a numerator to find the zeros of the first derivative, and there's going to be a denominator to figure out where the slope is undefined. So before we move on, we need to clean this up by ideally factoring things out. So let's factor 2 over 3 out, 2 over 3 out. And that leaves us with 2x 1 over 3 minus x negative 2 over 3. This is not fully factored. I just want to factor out the constant first. Now the next thing is we're going to factor out the x. But which x? You want to always divide out the smallest x. The smallest x with the smallest exponent. Now between 1 over 3 and negative 2 over 3, which is a smaller value, negative 2 over 3. So in other words, I'm going to divide everything by x divided by negative to the power of negative 2 over 3. So I'm just showing, the red part is just showing you my work, and I end up getting with the following. So when you have same bases and you divide, what do you do with exponents? You're going to subtract. So 1 third minus negative 2 3 becomes plus. In other words, you're going to get x to the power of 1. Now, in this particular case, we end up with same divided by same gives you 1. So over here, what we have here, just factor out the negative 2 over 3, is our factored form. So let's just clean it up a bit, just make it look more nicer looking. X 2 over 3 negative 2x minus 1. And now I'm going to change this to a rational-like function. So I know that 2x minus 1 belongs on the top, but the negative exponent means you have a x to the power of 2 over 3 at the bottom. So now we have a rational irrational function. So now we can figure the critical numbers. So remember what critical numbers means. F prime is 0 or F prime is undefined. To find F prime is 0, we're going to look at the numerator. So you have 2x minus 1 equals to 0. For undefined, you're going to look at the denominator. You're going to set it to undefined. This gives me 1/2, and this gives me 0. And let's figure out whether we can get a y value out of this. I don't want you to think that just because you have something from the denominator, it necessarily means it has to be a vertical asymptote. It may not be the case. This just means where the slope is undefined. It doesn't tell you where the x value of the function is undefined. So let's figure out whether we can get a y value. And if I sub 0 back into here, I'm going to get a 0. So that means this is a point, and it's actually a dot. Over here, 1/2, we do the same thing. We're going to get some sort of number, whatever that may be. So the next thing we're going to do is classify them. First derivative test again. So let's set this up. So over here we have the 0, and we have 1/2 from lowest to highest for the critical numbers. But here you can put the entire derivative here, and we just put in numbers here. So now the question right now is 0. We can call it undefined. Here the slope is 0, And if you put numbers like -0.5 or 0.25 here or 5 here, you're not getting the following: negative, negative, and a positive. So that means this goes down, and goes up. Now, based on what I have here, what can we classify this point here? Well, it goes down and down. It is not a turning point because a turning point must go down and then up, or the other way around. Half. So this is no classification. This one here is going to be a turning point because it goes down and then up. Therefore, it is a local minimum. So here we have the graph of the function that we just did, and let's analyze the critical numbers. So our first critical number was over here in blue. That was at the origin, 0, 0. And the other critical number was here. And we just established that at this point over here, it was a turning point of a local minimum. And now let's just actually look at the origin. So remember in the first derivative test, the slope was negative, so it's going down to the left. Over here to the right of this dot here, it's also going down. And the question right now is, well, what is a graph with a defined point with a undefined slope look like? Well, recall in the past, if I were to draw a tangent here, it would be a vertical tangent. So what that means is this dot here is not a turning point, but it is a vertical tangent because the point is defined and there is a undefined slope.